New unit day here at AP Chemistry. We got unit 2 now. It's about 10% of the unit, of the exam. The unit's about 10% of the exam. And it's going to take somewhere between 2 and 3 weeks to do. There are only, It's either 7 or 8 learning targets to get through. So this will go a little bit faster than last unit. We'll probably spend a day or two on Lewis structures just to make sure everybody is at the same place, but not as long as the first unit. So here we go. 2.1 is types of chemical bonds. So this is basically the difference between ionic and covalent compounds. There's many different ways that you can figure out the type of covalent bond. You can use electronegativities to figure that out. You can also use basically the composition of the atoms and the type of atoms. So this basically says what electronegativity is. Electronegativity is the atom's attractedness to the electrons in the chemical bonds. So if we think about a carbon atom, if I can find a whiteboard marker here that works. We have a carbon atom here, bonded to a hydrogen atom, and then we have 2 electrons that are in that chemical bond. These 2 electrons are going around both nucleuses. It's not a perfect oval like this. It's doing a bunch of weird stuff which you don't actually have to know about, but the point is that these 2 electrons are going around both of these nucleuses. Since these elements are in different energy levels, hydrogen is in the first energy level, carbon's in the second energy level, and since they both have different nucleuses, hydrogen's nucleus is +1, carbon's nucleus is +6, these 2 electrons are not going to be perfectly attracted the same amount to both of these nuclei. These electrons are going to be attracted to one of them more than the other. And it doesn't just matter about the charge of the nucleus. It also matters the size of the atom. So things get very complicated, which is why they just use the trend of electronegativity. The trend of electronegativity, basically the more attractive a nucleus is to an electron, the higher the electronegativity. So if you think of the periodic table, all you have to know for that trend is fluorine is the highest, which then means that francium is the lowest. So as you go this way, it goes up in electronegativity, and as you go this way, it goes up in electronegativity. The noble gases, at least the top 3 ones, do not form chemical bonds, so they are not included in electronegativity tables. But the bottom few noble gases usually are, because if you heat them up hot enough, they can form covalent bonds. Great. That's what that says. Valence electrons shared between atoms of similar electronegativity constitute a nonpolar covalent bond. So if the nucleuses are similar, and let's use an extreme example where the nucleuses are exactly the same. This is the fluorine molecule, F2. These 2 electrons are going to be evenly distributed around these 2 nucleuses, and so we call that nonpolar, because the electric charge will be evenly distributed around the entire molecule. So if they have similar enough attraction to the electrons in the bond, then the electrons will orbit the 2 nucleuses. You can see it say nucleuses or nuclei, both are correct, roughly equally. This results in an equal distribution of charge across the chemical bond, and we call it nonpolar. This delta means different in, so when you're looking at a table of electronegativity values, you subtract the 2 numbers from each other, and if these are the same nucleus, they have the same electronegativity value, so it's a number minus itself, which equals 0. So the difference in electronegativity between these 2 atoms is 0. If it's anything less than 0.4, you usually consider it nonpolar. There's a few cases where it'll be exactly 0.4, where it's still considered nonpolar. Electronegativity is a really good guide, but it is not an absolute. There are numbers slightly above this that are still considered nonpolar for various reasons. You don't need to know those various reasons for the AP chemistry test. Okay, so here we go. So now they're not below 0.4. Now they're between 0.4 and 1.7. These are called polar covalent bonds. So these electrons are still going around both nuclei, but not evenly. And let's do another rather extreme example. So what are 2 elements that are pretty far apart, but not super duper far apart? Hydrogen and oxygen sound pretty good. So I forget the exact numbers of these, but the water molecule is a great example. So the oxygen here has a nucleus of +8, Hydrogen has a nucleus of +1 due to a bunch of different factors. Oxygen is more electronegative. So these two electrons are going to spend more of their time around oxygen than hydrogen because they're more attracted to oxygen's nucleus. They're still going to orbit around both nucleuses, nuclei, but they're going to spend more of their time around oxygen, which means that on average, oxygen will be a little bit negative compared to the hydrogen. And these little music note symbols are how you say a little bit. So it's not a full positive charge or negative charge because it's not a full electron. It's just a little bit positive or a little bit negative. So the greater difference in electronegativity lead to greater bond dipoles. So if we think of these as magnets, they have a positive pole and a negative pole, or a north pole and a south pole. Basically, the larger the difference is here, the stronger the magnet it is. It's similar to magnetism because these will produce an electric field because we have moving electrons. And if you know anything about magnetism in physics, magnets can produce both magnetic and electric fields. So they're similar. It's still an electrostatic attractive force. Okay, then this last one, the difference in electronegativity is not the only factor in determining if a bond is ionic or covalent. I think there's supposed to be another slide here. Basically, if it's more than 1.7, if the electronegativity is greater than 1.7, one of the nucleuses is so attractive to those electrons that it takes them completely. It's no longer just sharing them unequally. It has removed one electron from the other atom, and now it has it. Then it will have a full negative charge, and it is no longer a covalent compound, it's an ionic compound because you have a negatively charged thing and a positively charged thing. Keep that in mind. So the two numbers, you should probably memorize them, are 0.4 and 1.7. Some textbooks have this upper number at 2.1. That's just an example of the fact that these aren't set in stone, but these are the ones that I am most used to, and I believe these are the ones in your textbook. Okay, so then when you determine whether it's ionic or not, the electronegativity is only one factor that you look at. The best factors is actually the physical properties of it. So ionic compounds are solid at room temperature. Covalent compounds can be liquid, solid, or gas. The melting points of ionic compounds are generally high. Covalent compounds are generally low. If you dissolve ionic compounds in water, they will conduct electricity. Covalent compounds will not. Ionic compounds, most are highly soluble, some are not soluble at all. And covalent compounds, most have low solubility, some are soluble. Conducts electricity when dissolved in water? Yes, not usually. So whether it's in a liquid state, sorry, I misspoke here. If you melt ionic compounds, they conduct electricity as well. So whether it's melted, which is this middle one here, or dissolved in water, it'll both conduct electricity, and that's because the ions are free to move around. So in the solid state, the ions are fixed, and they're just vibrating a little bit. But when they're dissolved in water or liquid, those ions can move, and now you have electrical charges, the positive and negative ions, that can move around and transport the electric current. I think that's it. Nope, metallic bonds. Here we go. These are super fun. So metallic bonds, the model that's used in AP chemistry is the sea of electrons. So these pluses and the circles, that's basically the atom. So the plus is where the nucleus is. The circle is where the valence electrons are. And then the valence electrons are delocalized, so they can move around. So all of these nucleuses are identical, right? So these valence electrons aren't necessarily more attracted to any other nucleus in here. So the electrons can just kind of spin off and do whatever the heck they want. So if you think of the piece of metal as a tube, basically, it's a pipe that transports electrons. So the electrons are able to flow through the sea of electrons. They're called delocalized electrons. Every time you have a charged particle that's able to move around, you can transport electricity. Great. That's it. We're done. A+. Congratulations. Great job.